Howdy, folks. Welcome to day 4 of statistics, of Introduction to Statistics. What we did in, if you recall from day 3, is that we learned how to interpret a frequency distribution, which is a table, and we also learned how to interpret a histogram as a graphical frequency distribution. And what we're going to do is we're going to take the idea of a histogram today and we're going to push it a little bit further to a tool that is very useful in statistics. And this tool that I'm going to teach you about is not, it's sort of an introductory tool, just like a histogram, but it's more in the mainstream in terms of tools used by researchers when they use statistics. Okay. So here's, let me just recall, let's recall what we did the other day, is if we had a histogram like this one, there's 22 blocks. We have 5 classes. One class goes from 7 to 11, then 11 to 15, 15 to 19, 19 to 23, and 23 to 27. And there are 22 blocks, and so our scale is 1 out of 22. And so if I were to say to you, well, what proportion of the population that this sample comes from, I mean, just so you can recall what this 1 over 22 means, it means that our sample size was 22, that we had 22 observations, and that we organized them into this histogram. Okay? So we had a sample size of 22, but we're going to try and draw conclusions about the overall population. Remember, that's called statistical inference, when we take a limited set of numerical data, organize it, and then draw conclusions about the overall population. Okay? So if we were to say, well, what proportion of the population falls between 11 and 19 on this particular, or has observations that fall between 11 and 19 on this quality, well, we just count up the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's 13 out of 22. Okay, and we could turn that into a p, what we call a p-value. Let me get a calculator here. All right. Now we can turn this into a p-value by just dividing. If we did 13 divided by 22, we would get 0.5909. So this indicates that the proportion, 0.5909, the proportion of observations in the sample between 11 and 19 is 59.09% or 59.1%. But as a p-value, we do those as decimals, it's 0.5909. So 0.5909 of the whole histogram is just in these 2 columns. The overall histogram is out of 1. So 0.5909 is less than 1. It's a portion of the whole thing. It's only 13 out of 22. So here's what I want you to think about. What if we, what would happen if we, instead of taking only 22 observations, what if we took a large number of observations? What if it was 22,000 instead of just 22? And what if everything on here just sort of increased by 1,000? So instead of this being 1 observation, it's 1,000 observations. And this is another 1,000 observations. So instead of this column of the histogram being 2, it's 2,000. And instead of this column being 5, it's 5,000 and 8,000 and 5,000 and 2,000. Our scale would not be 1 out of 22. It would be 1 out of 22,000. Okay? So here's what I want to show you is some of the histograms you did not look this pretty. You know, we might have had this side went up here and this side went up here and the middle might have been flat with this. They were not symmetrical. And this is an important conceptual idea. Here's the idea, is that if a population has certain qualities, and we'll discuss those qualities later, then as the sample size becomes larger and larger, instead of just 22, if it was 2,000 or 5,000 or 20,000 observations, what happens is the histogram starts to take on a much more uniform look. it actually starts to look symmetrical, where it's even on the left side and the right side. And that's called the law of large numbers. Well, it's based on the law of large numbers. The law of large numbers says, law of large numbers. And here's what the law of large numbers says. It says, as the sample size becomes large, meaning a large number of observations, as the sample size becomes large, the sample distribution approaches, it becomes more like, approaches the population distribution. Okay? All right, so the law of large numbers says that as the sample size gets larger and larger, this histogram will actually start to look like the real histogram that you would have if you had observed every item in the population. Okay? So that's the first thing I want to show you, okay, is the fact that as your sample size gets larger and larger, your histogram is going to start looking a lot more uniform. It's going to start to become symmetrical. Now, again, this is assuming that the population meets certain criteria, and we're not ready to talk about those criteria right now. We will in just a little bit, okay? So now, here's the other thing that I want you to do mentally, is I want you to sort of pretend that this histogram, instead of having classes that are 4 wide, instead of from 7 to 11 and 11 to 15, 15 to 19, 19 to 23, 23 to 27, instead of having classes that are very wide, okay, here's what I want you to do, is we're going to cut the histogram, the classes up into thinner pieces. And I don't just mean from 7 to 8, not just from 7 to 8 or 8 to 9 or 9 to 10. We're actually going to cut them up into hundreds of pieces to where these blocks, instead of being 4 wide and not even 2 wide or 1 wide, where we're going to make them like 0.01 wide, so that there are like maybe 400 columns between here and here, and 400 between here and here. And here's what would happen, is as the blocks get thinner and thinner, they stop looking like blocks so much, and they start looking like lines instead. They become so thin that they're basically a straight line instead of a rectangle, okay? And when that happens, kind of like if you think about a TV or a computer screen or the screen of your phone or something, you know that that screen is made up of a bunch of tiny little squares called pixels. But they don't look like squares. Because there are so many of them, they look just like dots. And when you put thousands or millions of them together, it looks like a smooth image, a smooth picture, okay? And so watch what's going to happen is if we did make all of these little classes thinner and thinner so that they're straight lines, they won't look blockish like a ziggurat. They would actually start to smooth out and look more like a curve. They would look curvy, okay? And when that happens, it becomes what is often referred to as a bell-shaped curve, a bell-shaped curve. And that's what I have drawn right here. This is a bell-shaped curve. And we refer to this bell-shaped curve in statistics if it meets certain criteria. We call it a normal distribution. So it is a frequency distribution, but it's a very special kind of frequency distribution that is curvy, and we call it a normal distribution, or we say that the observations are normally distributed, and that's the assumption. See, this would only happen if the observations in a population are normally distributed, and not all populations have normally distributed populations. But we're going to save that for later in the semester, or maybe for your next statistics class. Okay? Actually, later in the semester, we are going to get to some distributions that are not normal distributions. But most of what we're going to do in this class, in this semester, is going to be based on normally distributed data. Okay? So here's what we're going to do. Now that we have the normal distribution, we're going to assume we've got hundreds of little tiny lines here that are like histogram columns. But there's thousands of them from all the way over here, all the way over to here. And they go to positive infinity and they go down to negative infinity. Okay, that's what this curve is doing. So now, because of that, we no longer need a histogram anymore. Also, okay? And again, this is based on, a part of this is based on the law of large numbers. Okay, is that what we're assuming this, and we could be wrong, but we're assuming that as the sample size becomes large, the sample distribution, this little histogram we had, starts to look like the population distribution, which has possibly hundreds of thousands or millions of observations, and they would fall under this curve. So now the rest of what we're going to learn today is basically, I'm just going to teach you how to use, I'm going to teach you the beginning of how to use the normal distribution curve as a tool. The first thing I'm going to teach you is I'm going to teach you how to make a normal distribution curve using a mean and a standard deviation. And that's all you need, is just a mean and a standard deviation. So let's say the mean of a sample is, let's say it's 20. And let's say the standard deviation is 3, okay? We can take that information and we can create a normal distribution of that population. And it's real simple. Basically, you just put the mean in the middle, so we'll put a 20 here, and then see these 3 marks going up? Those are standard deviations. This is 1 standard deviation, 2 standard deviations, 3 standard deviations. Going this direction, we're going 1 standard deviation backwards, 2 standard deviations backwards, and 3 standard deviations backwards. So, since the standard deviation of this set of data is 3, what we're going to do is we're going to add 3 to the mean. So the mean is in the middle, that's 20. Then we go up 1 standard deviation, so we're going up by 3, so this becomes 23. Then we're going to go up by 3 again. So up 23 up by 3 becomes 26. 26 up by 3 becomes 29. Then going this direction, starting at 20, and then going down by 3, 20 minus 3 is 17. Then down by 3 more is 14. Then down by 3 more is 11. And what you now have here is a normal distribution based on this data from a sample where the sample mean is 20 and the sample standard deviation is 3. Okay? All right, let's do another one. Okay, let's say that you're given a mean of 67 and a standard deviation of 3.8. What I want you to do is do what we just did and draw your bell curve and then put the correct numbers on all these lines. Pause the video and try it. All right, so let's go ahead and see how you did. What goes in the middle? The middle is the mean, so that's 67. Then we're going to go up by 1 standard deviation, which is 3.8. And 67 plus 3.8 is 70.8. Then we're going to go up by 3.8 again, and we're going to be at 74.6. Then we're going to go up by 3.8 again, and we're going to be at 78.4. Now for these 3 marks over here, minus 1 standard deviation, so we're going to go down by 3.8, so that's going to be 63.2. Then we're going to go down by 3.8 again, and that's going to be 59.4. And then we're going to go down by 3.8 again, and that's going to be 55.6. Okay? And so what you're looking at here now is the normal distribution curve where the mean is 67 and the standard deviation is 3.8. Okay? Let's do one more example. All right, let's say that the mean of the population, the mean of the sample, which we don't, in many cases, we don't know what the actual population mean is. So in many cases, we have to use the sample mean as the population mean because we don't know what the real population mean is. Okay? But in this case, let's use the sample mean of 243 and the sample standard deviation of 17 and go ahead and try and create a normal distribution curve. All right, let's see how you did. We're going to put the mean at the middle, 243. Then we're going to add 17. That's going to be 260. Then we're going to add 17. That's going to be 277. Then we're going to add 17 again, and that's going to be 294. Then going the other direction, we're going to subtract 17, and that's going to be 226. Then we're going to subtract 17 again, and that's going to be 209. And then subtract 17 again, and then that's going to be 192. And so what we have here now is the normal distribution curve where the mean is 243 and the standard deviation is 17. Okay? All right, now what we're going to do is I'm now going to teach you an important introductory tool that makes use of the normal distribution curve. Okay? All right. So let's actually, you know what, we're going to keep this distribution curve. And what I'm going to teach you is called the empirical rule. The empirical rule. Okay? It is also sometimes referred to as the 68, 95, 99.7 rule. Okay? So, here's what the empirical rule says. Remember how with the histogram we were identifying the proportion, the proportion of the frequency, and we would count up the blocks. And remember we counted up 13 blocks out of 22, and we came up with a p-value of 5909, 0.5909. Okay, so here's what we're going to do. The purpose of the normal distribution curve, or one of its uses, is we can use it to identify the proportion of observations in a population that are between two values in the population or less than the population or greater than a number in the population. Less than a number in the population, greater than a number in the population, or between. Here's what I mean. Let's say that we wanted to ask the question, what percentage or what proportion of all the people in the United States are between 5 foot 7 inches tall and 6.3 inches tall? Okay? And so what we could do is we could find out what the mean height of people in the United States are and the standard deviation of the heights of the people in the United States, and we could put them on a normal distribution curve. Now, this is assuming that the heights of people in the United States are normally distributed across the population. Okay? Now, if that was true, we could then say, we could find out where the number 5 foot 7 inches is, and then find out where 6 foot 3 inches is, and find out what the proportion is between, just like the histogram, as if there were little blocks here, right? As if there were blocks. Now, there aren't blocks here, but we could pretend there were blocks here and count up the blocks and get a proportion, just like we did with the histogram. Well, the empirical rule will help us with those percentages, with those proportions. And this is what the empirical rule says. It says that 68%, that 68% of all observations in a population fall between -1 standard deviation and +1 standard deviation from the mean. That 68%, now technically since we're talking about a population, we would be dealing with mu, okay? But we got these numbers from a sample, or we made them up. So 68% of all that's why it's called the 68, 95, 97.7 rule. The first one, the 68, that means that 68% of all observations in a population are going to be within -1 and +1 standard deviation from the mean. So given these numbers right here, if I said what proportion of all observations in this population are between 226 and 260, the answer would be P equals 0.68, because that's the same thing as 68%. So, now here's the thing. Because we also have the mean, I'm going to draw a vertical line here at the mean, then I'm going to draw a vertical line here at the -1 and 1 at +1 standard deviations, okay? And here's what I'm saying. 68% of the observations are between -1 and +1 standard deviation. Now, the normal distribution curve is symmetrical. That means it's a mirror image on the left and the right. It's equal on the left and the right. So what we can do is we can take the 68% from here to here, and since the mean is in the middle, we can cut 68% in half. So 68%, let's say 0.68 divided by 2, if you did that in a calculator, you would get 0.34. And what that means is that in each one of these regions right here, it's 0.34. The probability or the proportion is 0.34. That's the first part of the empirical rule. The second part of the empirical rule says that 95% of all observations fall between -2 and +2 standard deviations from the mean. So now if I create more regions here, if I do this, and if I do this, okay? Starting at this line and going all the way up to this line is 95% of all observations. Now, we already have 68% in the middle. So, if from here up to here is 95, but we already accounted for 68 in the middle, we're going to take our 95% and subtract 68%, and we get 0.27 or 27%. So, these two little regions here add 27% onto the 68%. And if we cut this 27% in half, it becomes 13.5% or 0.135. And we're going to put that 0.135, half of it in here, the half of the 27% here, and we're going to put the other half of the 20% in here. And now, if we were to ask the question, what proportion of the observations are between 226 and 277, all we have to do is add up the regions in between those numbers. Add this and this and this. So in a calculator, we would add up 0.34 plus 0.34 plus 0.135, and it would give us the p-value would be 0.815. So from here over to here, 0.815 of all of the observations, or 81.5% of all observations, are between 226 and 277. Okay? All right, let's do the last part of the empirical rule. The last part of the empirical rule says that, so we have the 68, 95, and then 99.7. The last part of the empirical rule says that 99.7%, now that's almost all of them, right? 99.7% is almost 100%. So what we're saying here is that almost all of the observations within a population are going to fall between -3 and +3 standard deviations from the mean. Now, 95% of this is already accounted for in the middle here. So we need to take our 99.7 and subtract 95. 95, and that gives us 0.047, or 4.7%. Now, we got to cut that in half because half of it is over here in this little region, and the other half is over here in this little region. If we divide that by 2, we get 0.0235, or 2.35%. And what I'm saying now is that this little region here accounts for 0.0235% of the entire population, and this little region here accounts for 0.0235, or not 0.0235%, but 0.0235 of the population. So if you add up this plus this plus this plus this plus this plus this, you'll get 0.997, or 99.7%. Okay? Now, what that leaves now are these two little areas in the ends. Those are called tails. T-A-I-L-S. Tails. In fact, don't they look a little bit like tails, like a lizard's tail, one in each direction? There's a little bit left in the tails. Since from -3 standard deviations up to +3 standard deviations accounts for 99.7%, that leaves 0.3%, which is 0.003. And since there's two tails and it's symmetrical, we got to divide it by 2. So we're going to divide by 2, and that gives us 0.0015. And that is what's in the tails. 0.0015 in there, and 0.0015 in there. Okay? And that is the empirical rule. Now, what I'm going to do is I'm going to clean up the board here. I'm going to leave that, the percentages, and I'm going to erase those numbers. And what I'm going to do is I'm going to show you how to answer some interesting questions using the empirical rule. Okay, so now we've got our normal distribution curve here. The empirical rule says that 34% of the observations are going to fall between 0 and 1. 34% are going to fall between 0 and -1. 13.5% of observations are going to fall between 1 and 2, and 13.5% of observations are going to fall between -1 and -2. 2.35% are going to fall between 2 and 3, and 2.35% are going to fall between -2 and -3. 0.15%, or 0.0015 p-value, is going to account for all values greater than a standard deviation of 3, and same value for less than a standard deviation of -3. So here's the kind of question you're going to be asked. Let's say that there's that you take a sample, and the mean of the sample is 15, and let's say that the standard deviation is 2. And here's the question. What you're asked is, what proportion of the population, remember, we're going to use the sample statistics to draw an inference about the population. What proportion of the population has an observed value less than, let's say, less than 11. Well, in order to answer this question, let's first put our numbers. Let's create our normal distribution. The mean is 15. Standard deviation is 2. So we're going to go up by 2, 17. Go up by 2, 19. Go up by 2, 21. Go back to the mean. Go down by 2, 13. Go down by 2, 11. Go down by 2, 9. Okay? And so the question is, what proportion of the population has an observed value less than 11? So we're going to go to 11. Here's 11. And we're going to look at, we're going to add up all of the proportions in these regions less than 11. Well, we've got this region plus the tail. So all we have to do is add those two up. 0.0235 plus 0.0015. And if you add those together, you get 0.025. And so the proportion is 0.025, or 2.5%. So P equals 0.025. That's the proportion of the population that has an observation that's less than 11. Okay? All right, what if we were to ask the question, what proportion of the population has an observed value more than 17? Or greater than 17? Okay, so what we're going to do is we're going to go to 17, right here, and we're going to add up all of the values that are larger than 17. So we're here, and we have three regions. We have this region, and then the tail. We're just going to add them all up. 0.135 plus 0.0235 plus 0.0015, and when you add those together, you get 0.16. 0.16, and so the answer is P equals 0.16, and we're done. See, all you're doing is you're just adding up these regions where you know the proportions based on the empirical rule. We're going to do one more example, and then I think you're good to go. I think you'll understand it. Okay? So let's say, what proportion of the population has an observed value? We're going to do a between here. Has an observed value between, let's say, 13 and 19. Between 13 and 19. Well, here's 13 right here, and here's 19 right here, and so all we have to do is add up all the regions in between. We have this region, and this region. So we're just going to add those three up. 0.34 plus 0.34 plus 0.135. And that's going to be equal to, let's see, 68, 78, 81, 81.5. So 0.815. So the answer will be P equals 0.815. And that's it. That's how you use a normal distribution curve with the empirical rule to make, now this is really mundane, this is a low-level inference level. Or you're just, really the only reason you're learning this mostly is so that you can begin to get an idea of how this proportion under the curve works. In the next class, we're going to dig into a much deeper, more granular way of looking at these probability proportions, okay? But you have to be able to do this. You have to get this into your brain to be able to make the next step, okay? All right, well, good luck, and I'll see you in the next video.